Hi, this is an example problem from Chapter 18 on the electric field from point charges. This problem is actually the same as the previous problem, net electric static force 1D, but it uses the electric field to determine the force, and so you should compare those two approaches here. Pause for a moment and read the question. Okay, so I've kind of set this up a little bit. The picture there, you see it familiar from before, but we're missing a charge at the origin point P. What we're asked to do in this case is to calculate the electric field at point P, and that electric field is going to originate due to Q1 and Q2, which we consider the source charges of that field at point P. Now I've gone ahead and drawn the straight line distance from Q1 to P and Q2 to P and identified how far those are. When you have a point charge, the magnitude of the electric field is given by an equation which is based on Coulomb's law. It's Coulomb's constant K times the magnitude of the point charge, that's the source of the field, divided by the distance from the point charge to the point in space where the electric field is going to exist. Now when you have more than one sources generating the field at that point P, then you need to add those electric field vectors using vector addition. First step, of course, though, is to calculate the magnitude for each of these. So let me go ahead and calculate for the electric field at point P due to charge Q1. K 9 times 10 to the 9th coulombs, oops, not that, newtons, meters squared per coulomb squared, multiplied by the magnitude of Q1. We see that that is negative 33 microcoulombs. In that case, the magnitude is 33 times 10 to the minus 6th coulombs. And the distance there from Q1 to the point P, 0.21 meters. And I see another mistake in the equation there. Should be squared. Plugging this into the calculator, we come up with 6.74 times 10 to the 6th. And if we look at the units here, we're going to go ahead and cancel out our meters. And we'll cancel out one of the coulombs on the bottom. So we are left with the units of electric field, which are newtons per coulomb. Now for this one, this is a negative 33 microcoulomb charge, and we need to figure out the direction of that electric field, because this is 6.74 times 10 to the 6 newton per coulomb. That's the magnitude, the length of the vector, if you want. Now we need to figure out the direction. The way that we do that is we imagine putting a positive charge at point P. This is just something you make up in your head to get the sign correct. If I were to put a point charge positive at point P here, which direction would it be? Pushed or pulled, attracted, repelled by Q1? Well, it would be attracted, right? So the direction of that electric field is going to point straight up. That's the electric field at P due to charge 1. So I should write this as P due to charge 1. All right, let's go ahead and do the same thing here for the electric field at point P due to charge 2. We're going to go ahead and use the same equation as before here. Only this time we will do charge 2. Plugging those numbers in. In this case, we've got charge 2 is plus 42 microcoulombs, so that's going to change this to a 42. And this distance here is going to be 0.36. We go ahead and put that into the calculator. We get a value of 2.92 times 10 to the 6th newtons per coulomb. And to draw that electric field vector. Again, we're going to assume, just in your mind, pretend you had a positive charge there at point P. What would be the effect due to its interaction with Q2? Is Q2 going to repel it or attract it? Well, Q2 is positive, so that imaginary charge at P that's positive would be repelled. Therefore, we know the electric field is going to point straight down. And it's about a little less than half the length of the other one. So draw it about like this. The electric field at point P caused by source charge 2. Now we need to go ahead and add up these electric fields to get the net electric field. And I'm going to go ahead and just use my table here, because this table approach works whether you're doing 1D or 2D. Helps you organize the components of your vectors. And in this case, we know that for the x-axis, everything's going to be 0. This is all y-axes here. So we've got the electric field at point P due to charge 1, the electric field at point P due to charge 2. Neither of those vectors point anywhere along the x-axis, so these are both 0. And for the y direction, all of the vectors are on the y-axis, so I'm going to get the sign by looking at whether they point up or down. EP1, y component is up, EP2 is down, and then all of the magnitude is along the y-axis, so I can put the number in there. So for 1, it's 6.74 times 10 to the 6th newtons per coulomb, and for the other one, 2.92 times 10 to the 6th newtons per coulomb. And to get the net electric field, or the total electric field at point P, I need to add the components. We're doing vector addition here, right? So essentially this is what we're saying. It's the superposition principle. I need to add all the different contributions to the electric field at point P to get the total electric field. And since they're vectors, it's vector addition. Adding the x components, we get 0. And adding the y components, we get 3.82 times 10 to the 6th newtons per coulomb. To complete part A, we need to calculate the magnitude and specify the direction plus or minus along the y-axis. Well, in one dimension, since the y component is positive, that is our magnitude. But let's go ahead and replot this again just to kind of see this a little more clearly. All right, so here's our picture again. And so now that we've added these vectors, we can replace these two with the single vector EP. And we know that in this case, that single vector EP, it points straight up. And I just told you that the magnitude of EP, of course, is 3.82 times 10 to the 6th newtons per coulomb. And if we want to use this directions up or down along the y-axis to specify the direction of the vector, we can write plus. And so there's the electric field at point P. Now for part B, we're going to get the same answer as we did in the earlier problem, net electrostatic force in 1D. And notice that we just did it a slightly different way. So in this case, we're asked, let's put a third charge, Q3, at point P and figure out what force it experiences. Okay, here's my third charge. I'm going to place it there, Q1, Q2, the source charge is still there. Q3 is equal to plus 9.8 microcoulombs. And to calculate the force, since we know what the electric field is at that point, we just use this relationship relating the electric force to the electric field and the charge placed at that point where the electric field is located. In this case, we can go ahead and directly plug in our values. So Q3 in this case is equal to plus 9.8 microcoulombs, and E is equal to plus 3.82 times 10 to the 6th newtons per coulomb. Putting this to calculator gives us a force on charge Q3 equal to positive 37.4 newtons, where the positive sign means it points up towards plus y axis. And that makes sense because we know that a force, if it's a positive charge placed at the electric field location, then the force is in the same direction as the electric field. And so that's the case here. Just one thing to be sure that we canceled out our coulombs, and when I did my calculation, I included this times 10 to the minus 6th for the micro. And then we end up getting this value here.